So, welcome to the second lecture of the 5th week. It is on multiple integrals. It is very important that I tell you certain things right at the beginning, that if you have seen me drawing a domain D, if you have seen me drawing a rectangular domain, please understand that we are always integrating or finding double integrals over a closed and bounded set, a set which has something inside and it has boundaries. In mathematical parlance, those who know some bit more of geometry or topology would understand that these sets are called compact sets. Any closed and bounded sets in R2 are referred to as compact sets. Our domain has to be a compact set. It cannot be that okay, it has a boundary or it does not have a boundary or it just goes open in one direction, that I can be in the set and remain in that set forever. We would be looking at those sets so that I cannot start from a point in the set and move in any direction and remain in the set forever. For example, if you look at the first quadrant of in R2 called R2 plus, that is a set of all coordinates x, y, where x is bigger than or equal to 0 and y is bigger than or equal to 0. Start from any point 1 1 and you move along the line y equal to x, you go to 2 2 3 3 4 4 and you keep on moving, you will still continue to remain in the first quadrant. So such type of things, such type of sets we will not consider while we are learning multiple integration now. Those are improper integrations, though we will not consider it here at this moment at your level. We are not going to delve into such issues right away here. So, I want to say that whenever we are talking about domains of integration, the domains of integration has to be closed and bounded. Now, we have tried to understand in the last class the double integral. We interpreted our non-negative function over a given domain D as a volume under the graph with the domain D as one of its end surfaces. We had done some integration on the rectangular domains, and now of course we figured out that we can interpret that also as a volume. So, we started looking as we moved in the last class, if you have observed, we had started coming into more and more rectangular domains. So, it is much more easier to handle. Now, this allows us, this would force us to make two different significant notational changes. One is that when I am using rectangular domain, I will use the symbol R. When I am using a symbol R, means I am talking about rectangular domain, that is, it is the Cartesian product of two closed intervals in R. And D, any closed and bounded domain. So, this is very important to keep in mind, these two symbolical stuff that I am writing down, because that is what I will follow through. Yesterday, even for the rectangular domain I wrote D, because we were talking on general domains, and then we said okay, you can have, if the scenario is rectangular, you can write it as iterated integrals and all sorts of things. We have not told you how to handle the double integral over a general domain using iterated integration, that we will come next. So, first what I will do is that knowing what we mean by fx, mean by the integral of a non-negative function over a rectangular domain, which is a volume contained under it, volume of the solid contained under it, we go on to define now the definition of any bounded function, any function f of x y which is bounded on a given rectangular domain R. How would I go ahead and define the integration? Okay. How will I define an integral? So, my scenario is, I will just not use the board that much today. So, my scenario is the following. I am trying to now talk about the way which Riemann would do, but in, so we are talking about Riemannian integration in 2 dimensions. So, here is my rectangular domain. I am drawing it like this, but it has all its boundaries given. There is the x axis, there is and this is my rectangular domain R. Now, how do I start integrating on it? So, now I will consider a function f from R2 to R and assume it is bounded. I do not bother much whether this function is bounded, whether this function is non-negative or not, and I seek to find the definition of the integral over a given rectangular region of fxy dy dx. I seek to find a meaning to this integral. What does this integral mean? That is the thing that I want to seek and find. Can I do some kind of a partitioning? You might say, okay, it is not a big issue. How will I do that partitioning? So, let me do one thing. I divide this, I will draw some lines parallel to the y axis within that rectangular zone. Of course, you can say take the function f to be bounded only in the rectangular zone, that would also do, but we are just making life simpler and simpler. And then draw some lines parallel to the y axis, x axis. So, what we have formed is a rectangular grid. And in that rectangular grid, I would know the area of each rectangular grid. So, take, for example, take this rectangular grid and take any point C from here, C. So, I will look at FC into the area of the grid. So, function value into the area of the grid, that is what I will do, kind of constructing a kind of cylinder or a parallelepiped, and that's trying to construct such a thing. So, this I will do for just one of them, and actually I will do for all of them. I will take some arbitrary point C and then I do it for all of them and get my, and then sum that, and that is an approximation of this integral. Then I take much more and more. I see here there are number of cells, right. For example, here you can count what the number of cells are. Then I can keep on increasing. I am basically the partitioning that I have here on this side of the rectangular domain and this side can increase, and the number of cells would increase and hence the sum would become more and more and more refined, it will be more and more near to the integral, and then in the limiting sense we can define that limit as the integral itself. It is exactly the partitioning process what we see for Riemann integration, and that partitioning process we will explain it. Now we will be much more in more detail. So now what we can do is to consider R, the rectangular zone is expressed in terms of the Cartesian product of two intervals, which anyway this rectangular zone that you see drawn here on the screen is also of the same type, that is the one you see in the screen. And here what I can do, so what would happen is that you now partition AB and you partition the side CD in equally spaced intervals. So here is my x axis, I am keeping everything on the x on a positive side, does not matter, it is all, it may not be positive. So here is my AB, A and B, and here is my CD. So this is my rectangular zone. So what I do instead is I partition AB with starting x0, x1, x2, xi, xi plus 1 and to this is xn. So AB is the partition of AB, partition AB consists of points A equal to x0, x1, x2, xi, xn equal to B. And now they are equally spaced. If there are n such points, right, there are n plus 1 such points, so there are n such gaps between them, n such intervals. So if they are equally spaced, then the length must be divided by the number of intervals you want. So your interval length h, say h1 say, because I am taking it on AB, h1 the interval length is given by, for any xi plus 1 minus xi by, sorry, interval length is given by the total length b minus a divided by n. Basically what is happening is that you take any interval xi plus 1 minus xi is equal to b minus a by n. A similar partitioning you can do of y with starting your y naught at C and ending with yn at D. So these start with this as y naught and then put y1, y2 dot dot yj, yn. So in that case the partitioning of CD is equal to C equal to y naught, y1, y2, yi, yn equal to b, with h2 the gap is nothing but d minus c by n. That is, you can always write here that yj plus 1 minus yj. So, j is equal to 0 to n minus 1 actually. Or maybe I can write this as j and put that as k, that does not matter. I put I and that is j. So, okay. So, here this distance is nothing but d minus c by n. So, this is what I have done. So, what I do now is corresponding to this through x1 I draw a line perpendicular to the x axis at x1 which will become parallel to the y axis, through x2, through xi, through xi plus 1 and so on and so forth basically, and the same thing. Okay. We are assuming that it is bounded. So, Rij is the rectangular zone formed of the Cartesian product of xi plus 1 cross yi plus 1, yi plus 1. This gives me say xi plus 1, this one which say some yj plus 1, this zone, this one, this is yj plus 1. So, this one, this gives my rectangular zone Rij. This gives my rectangular zone Rij. Okay. I think that is clear, that is visible. I have no clue on the sign of the function. So, I am constructing a sum, the nth sum. So, I am taking any point Cik from Cij from Rij. So, for each such I and j, so I and j starting from 0 to n minus 1, f of Cij. So, Cij is some point here. So, this is your Cij, Cij is like a matrix formation, that is all. Cij, so Cij so f of Cij is into this is called the delta xi, the gap between these two into, so f of Cij into this area, that is delta xi into delta yj. So, xi into delta yj. What we are looking at is the following. What we are looking at is the limit, so this is called the Riemann sum. So, here of course, f is lying, you can obviously talk about an upper approximation and lower approximation because f is bounded by say capital M and has a lower bound small m. So, this whole thing is called a Riemann sum. So, it is a Riemann sum in the 2-dimensional setting, not in the 1-dimensional setting. It is Riemann sum to define a double integral of a bounded function. Okay. So, here what we are seeking is that the limit as n goes to infinity, that you keep on increasing the number of partition points, you make finer and finer and finer grids. This is called a grid. So, if we just take the rectangular region and take off this, just rub off this part of the drawing. then what you have formed is a grid. So, if you have more and more partitioning points, your grids would increase, the number of grids would become finer and finer grids. So, limit n tends to infinity, if this Riemann sum, if the limit exists, f of c I j into del x I into del y j, del x I into del y j. If this limit exists, and if it exists, this is called the integral over the rectangular region f of x y dA or dx dy or dy dx, whatever you want to call, or dy dx. If you want to say dy dx, you call it dy dx. It does not matter, whatever you want to. It is a symbol. This is just a symbol. This limit. So, you will understand calculus far better if you know at the very outset that every continuous function did not have a derivative. This is a very famous statement of Benoit Mandelbrot, the inventor of fractals, in one of the interviews given to Mathematical Association of America. And I would also say, taking a clue from such a great mathematician, that you would also understand calculus far better if you know at the very outset that integrals and derivatives are names given to special kinds of limits. So, integral is nothing but the limit of the sum. This is what Steve Strogatz calls as the infinity principle, an idea which was already known to Archimedes. That if the problem is big, you break it up into complicated problem, you break it up into smaller parts, look at each smaller part and sum them up and go to the limit and keep on making the smaller part smaller and smaller and smaller, and then in the limit, as you keep on doing it, wherever you are heading towards is your answer. So, that is the infinity principle, that is the guiding principle of calculus according to Steve Strogatz, and I kind of like to agree with him, because that is what happens all the time. Whole world actually runs on this thing. So, we have no idea how much this human civilization is indebted to this one subject called calculus. Now, what has happened is that this is what we will call the double integral. This is a definition for a general bounded function. You do not have to go into the geometry and into details of if you have a function of, if this is greater than or equal to 0, you can start defining things and all those things will come. One thing you have to understand, just like Riemann integrals, if in the rectangular domain, suppose here you have a rectangular domain, here is your rectangular domain. But along this closed curve, say C in the rectangular domain R, along this closed curve C, f is discontinuous. That is, f could have a kind of a strange looking graph. So, basically it could be like this. For example, if this is your R, so along C, so suppose you have a graph, if you have the rectangular domain, I am just writing it and trying to, so this is the x axis, this is 0, this is y, z axis. Suppose here is your C along which, so the graph could be like this, that okay, the sum part of the graph. So, here is the graph, but here it is not so easy to draw it. Let me just draw it up and then I will put the x axis. Somewhere here there is a gap, and then there could be other parts. So, there is a gap, and then there from here it picks up like this. Okay, so there is a gap here. So, here there is kind of a discontinuity. Only here in this zone, otherwise it is all. So, here the function value jumps up. So, let me, I think the drawing is not becoming. So, here some of the function value along this curve seems to, along this domain seems to have jumped up. Can you find the volume still? So, along this side the domain part should be, this drawing is taking a little bit of time, it is slightly harder. Suppose it has jumped up like this. So, can we still find the volume? What the Riemann's theory would say that yes, even in this case you can find the volume, we can still find the volume. Find the volume. Here I have taken positive functions. So, maybe I should draw the z axis at the back. Means we can integrate, means we can still integrate. And the double integral has a meaning. So, which means if you have a continuous function on a rectangular zone, the integral would always exist. If f is continuous, on a rectangular zone, or rectangular domain, then this integral f x y d of x d of y exists finitely. Actually, exists means exists finitely. So, that is the kind of idea that we are going to look at in a much larger scale. So, let us now go back and see that if this is my situation where I have this kind of thing, can I use an iterated integral idea to compute the integral? That is the question. But before we go, so we will write down certain properties of the integrals which are so obvious that I will not even give a proof of that. If you want to make a proof of that, you make a proof of that yourself, but I am not going to personally come down and go give you a proof of such things. So, here of course, I promised you certain things which will come up right in the portal, and they will come up, those promises will be kept. So, let us just write down the properties. So, you have a rectangular region R which is broken up into two rectangles equal to, I cannot say phi, and equal to a single line, that is R is R1 union R2, and maybe they share just one boundary as an intersection. If that is the case, then you can write that double integral R of f is double in, I am not going to write dy dx, I am just making a shorthand this time on this page. Double integral R So 1f plus double integral r 2f. This is just a shorthand I have put, that you should write, to be fully precise you have to write fx y dx dy. I am just not wasting the time. Similarly, if f1 and f2, f1 xy is less than equal to f2 xy for all xy in the rectangular domain. This rectangular domain is not the real number line. Please understand, real number line there is a double stand. So what I do is, now this would imply integral r f1 is always less than integral r f2. So these are quite simple consequences which, even if you think in terms of volume and all, you can figure out, but it is true for any kind of function. fxy is equal to k for all xy in R. Please understand that this k could be negative. Then the integral of f is nothing but k into area of R. Now you have two functions f1, f and g, and both has their integrals finite over R, and integral r f and integral r g exists. Then of course you have f plus g is integral r f plus integral r g. All these shorthands are because I want to put in a lot of stuff in this page. Of course, there is another thing which I am just giving on a side. If C is a real number, right, C is any R, C is in R. Now here R means a real number set. Then integral r c of f, if you multiply every value of f with c, is same as multiplying the integral and then integrating, then same as multiplying the integral of f with c. And the last one, that the absolute value of the integral must be less than the integral of the absolute value, which is a very, very basic result. That is what is the meaning. Of course, you can write x, y and all this, you can fill in the gap and make it look much more good. So here what it means, let me just draw, maybe some people might get confused by what I am meaning by R1 and R2. So this is R1, this is R2 and this is the whole R. So their union is R, but you know what, that their intersection need not be empty, the intersection is this line. So now we are going to this question of using the iterated integrals. This idea of iterated integrals that came from computing volumes using the Cavaliere's principle for non-negative functions. Can those idea of iterated integrals be extended to the case when we are talking about just bounded functions which need not be having non-negative values? Okay. So how do I do that? Can I evaluate it? So let us write down these very important results about iterated integrals. So iterated integrals and double integrals for general case. iterated integrals and double integrals relations in the case of bounded functions. If f from R2 to R is integrable in the rectangular domain. Integrable means that the limit exists and limit of that Riemann sum exists in the rectangular domain R equal to A cross B into C cross D, and if either of the iterated integrals we are not going to get into the details of proof etc. We are just going to give an example after we state this result, and you can try for the further things. Or integral A to B, integral C to D, fxy dy. If either of these iterated integrals exists, if either of the iterated integrals and if either of the iterated integral exists, then the value of that iterated integral coincides with that of the double integral. In fact, we then have fxy dx dy is integral A to B is integral C to D fxy dy dx integral same as integral C to D integral A to B fxy dx dy. So once you know this, you first have to check whether iterated integral exists. If somebody asks you to compute a double integral, just check whether the iterated over a rectangular zone, just check whether the iterated integral exists. If the iterated integral exists, then just compute that and equate it to the double integral. That's the story. That's it. You have to keep an observation that the function is bounded. For example, I am taking it from the book which we are using, so that I also don't commit mistakes, but I will take one example from the exercise also. So, compute integral r x square plus y dx dy where the rectangular region is 0 1 cross 0 1. So, let me do this 0 1. So, let me compute the iterated integral 0 1 x square plus y dx into dy. So, let us see what happens to this one 0 1 x square plus y dx. It becomes xa cube by 3 plus yx from 0 1. When you put 0 at 0, it is basically 1/3 plus y. You can try out the other form of other iterated integral. I will not try it, you and try it out for you yourself. And then you see, then I do 0 1 back to this part. So, I will have 0 1 y plus 1/3 dy, which when I compute finally will give me y square by 2 plus y by 3, 0 and 1. If I calculate it, the answer is 5 6. You can take the reverse one. You can, for example, check. So, for homework, not homework, if you wish to check, I hope nowadays people have checked the following. You would have some interest to check it up for yourself. This is just fun, just play around, nothing else. To play around and see that mathematics is actually working. What has been told as in the result actually holds true. So, if this iterated integral exists, so that iterated integral also should exist basically. So, 0 1, so do this. It is a very simple example I am computing and show that it is 5 by 6. Okay, that's kind of thing. Another example, I am using black pen because I am trying to do just as if I am doing some homework calculation. Take two functions f from ab to r, these are real valued function and continuous. So, it is integrable. Continuous means it is by Weierstrass theorem, it means there is a bound and the bounds are achieved. That is, these functions are bounded by Weierstrass theorem, it has upper bound and a lower bound. So, both are continuous. So, apply Weierstrass theorem to know that they are bounded. This is basic result in one variable calculus, see my course also. So, if I take the rectangular region R as AB cross CD, so there is exercise in the book trying to ask you to show that integral R and define phi xy as fx into gy. Okay. So, it is telling, show that this is nothing but integral a to b fx dx into integral c to d gy dy. That's, but it is again a very simple situation. So, here, so if this integral exists, these integrals exist, we are going to use the iterated integral technique. So, integral r fx into gy dx dy AB into fx into gy integral CD dy and this into dx. Now here fx would go out of the integration. So a to b fx into integral, this will become integral CD gy dy and this whole thing to dx. Now this, if you look at this, sorry, it will be gy dy. So fx would go out of the integration. So fx, because fx is constant here, so it goes out of the integration. So this now c to d gy dy integral, because it exists, it is finite. It will exist. The Riemann integral will exist. It is a continuous function, so the Riemann integral exists. So it is finite. So now this is just a number here. I can take it out. So it will become integral c to d gy dy into integral a to b fx dx. So that's it. So this is the use of the iterated integral technique, that if this integral exists and this iterated integral exists, because this iterated integral is this. This iterated integral is we have just write it equal to. So suppose we just don't bother about it. First we just write this iterated integral. So let us not bother about it. Let us just compute this iterated integral. If I write this iterated integral is the product of these two integrals which exist, and hence by definition, or by and hence by what we had written down here, we know that this simply means that this iterated integral, which is now equal to this, is actually equal to the double integral r phi xy. Basically first you just compute the iterated integral. If it exists, that is equal to the double integral. That is it. Here we show it exists because these two integrals exist, because these are just integrals of real valued functions, and any continuous function over a closed interval, the integrals exist. And with that we stop the talk, and next we are going to talk about double integrals but over general domains, but the general domain D, but the general domain will have a particular structure, and because those are the structures that come up in application, and we will talk about those things.